Well, thank you very much. I'm going to take about 20 minutes or so, and I am going to try to do two things. I'm going to try to remind everyone of the work that we've been doing for the DOE on large-scale regional simulations and why we think that's important, number one. Those that came to the 2021 peer workshop and forum, international forum, heard a lot of that. But a lot has happened since then. And the DOE Exascale Computing Project has progressed. After 6 years of effort, that project has come to an end December 31st of this year. And so we are in a transition mode from one that is development and developing compute engines, unprecedented compute engines, and transitioning towards application. And so that's why this workshop with all the people in the room and all the people online is very important today, because we're looking for feedback from the community with respect to the best way to make that transition. So I'm also going to talk about the 2021 Peer Pacific Rim Forum, and some of you may remember we had a number of action items and recommendations coming out of that workshop that were codified in a report. I'm going to hit on the highlights there, and the reason I'm going to do that is we really tried to solicit from 261 people who are participating in that workshop input on how to move forward. How do we take all of these very, very large simulations that we're computing on the world's fastest computers, and not everybody has access to the world's fastest computer, how do we take that and create a body of information that can impact both earthquake science and earthquake engineering? And so feedback from the community is very important. I want to acknowledge our supporters. The DOE Exascale Computing Project has been instrumental in developing our software over the last 6 years, a very focused effort. And so I'm going to remind us all what that was and what the objectives were. And I'll remind us the latest of where we've gotten to in terms of performance for regional scale simulations. I'll say what's a little bit different about that project, and certainly part of the reason we're up here today, is we put sort of equal emphasis on the earth science and the engineering, and how do you connect, what's the nexus between those two things in terms of regional scale hazard and risk assessment. I wanted to acknowledge that this is a joint effort between Lawrence Berkeley National Laboratory and Lawrence Livermore National Laboratory. We've had about a 10 or 12 person team working in this area for 6 years, intensely focused. And so we really couldn't have done that, and I'll talk more about this tomorrow, without this whole cadre of multidisciplinary team members, because doing this effort is not just earth science and engineering, it's also computer science and handling large amounts of data and some applied mathematics as well. And I'll go into that a little bit more tomorrow, but today I just wanted to hit the highlights, and let's begin by thinking about the remaining challenges to earthquake hazard assessment. And you're going to see, I've gone through the slides, and you're going to see this slide at least 4 times, but I'm going to preempt everybody because I get to use it first. What we're showing you here is the data that has been measured worldwide of earthquake ground motions, and this is directly coming out of the Peer NGA database. So you see on the right-hand side, and many of you have seen this figure before, but it's telling, if you think about the magnitude of the earthquake and the distance of which a earthquake measurement of ground motion is made, this is a cloud plot of all of those measurements that are embodied in the database of Peer. What do we see immediately? Well, we see in the yellow block here, the area that we probably care about the most, big earthquakes, and near the fault, we have the sparsity of data, which is not surprising. We just don't have a lot of big earthquake measurements. So the point is, we do our ground motion estimations based on empirical models historically by looking to the past, because that's what we've had to do, but that database is limited, particularly for areas we care about. And so that's where simulation, an argument for simulation in a moment is going to come into that. In addition, for many areas that we really care about, which have high hazard and risk, we have no measurements of historical big earthquakes. And a prime example is where we are today. You are here, that's a picture of the Berkeley campus, you can see the dot there. The Hayward Fault goes right through the stadium, and the Hayward Fault, if you parked in the parking garage up at the stadium, one of the recommended parking places, I'm just here to tell you, your car is right on top of the Hayward Fault. And so it's pervasive. The last major earthquake on the Hayward Fault was in 1868. Nothing was here then, as you can see in the lower left-hand corner. I think this was the one major building that was here, and you can see what's here now. That fault ruptures on average about every 150 to 160 years. Wouldn't surprise anybody if we had that earthquake right now. and because we're about 155 years into that cycle. So this is a really important area, and the reason I'm bringing this up is this is an area that we are going to focus our studies in the first realization of a simulated ground motion database. So we have the issues with risk, or hazard. We also have issues with risk, I would argue. And again, this is a motivation where we're going towards three-dimensional simulations and high-performance simulations to add understanding. For years, geotechnical engineers have assumed a 1D site response for the local site response considerations. And they've sort of done that without, in my mind, a really, really clear understanding of when that may go awry and may not be adequate or accurate. So 3D simulations can answer, or at least give new insight on some of these fundamental engineering questions as well. And so that's within the scope of what we're doing. So what do we do about these issues? Well, interest has really been growing in physics-based regional scale simulations. There's a number of groups around the world that are working intensely in this area. And this fall, there was an SSA meeting in Vancouver dedicated to this, and I'm sure some of you were there to understand the breadth of work that's going on. But the underlying notion is as follows. You have a regional domain of interest, like in the upper left-hand corner, could be hundreds of kilometers. What one would like to do on the right, upper right, is construct a representative and realistic model of that domain from an earth science standpoint as well as from an engineering infrastructure standpoint. And then you can play the what-if game and do the parameter studies and the understanding on a computer that we simply can't do given this dearth of measured data. So that's really the motivation that we're working towards in this work. On the bottom right-hand corner, the computational demands for this have been daunting. And so a big part of the DOE exascale computing project was trying to hammer down and overcome those computational limitations. And what we're leveraging here is the DOE's emerging GPU accelerated computer systems. And GPU systems are a fundamentally different architecture from traditional CPU systems. They rely on GPUs that can do parallel processing and calculations as opposed to CPUs that do things more sequentially. And so what I'm showing you here to give you a sense of where this is going, on the vertical axis is, just think of this as a measure of computer performance. There's a LINPACK set of operations that they use to test these computers. The lower scale is the year. What we're seeing is this inexorable increase in computational power, which is giving us an avenue and opening up the door to actually doing these kind of simulations, I would argue. And I'll show you some examples of that. The latest inclination of this is the DOE Exascale computer program, where they are trying to develop the world's first exaflop computer. And in fact, they've achieved that. So an exaflop computer is a machine that can do 1 billion floating point operations per second. And so the size of these machines, as you will see, and I'll show you some examples and applications, are really getting hard to grasp this computational power, but we need to harness that for this computationally intensive problem. So I would argue we're finally getting the computers big enough and fast enough to solve this problem. When I say solve this problem, from our standpoint, we're talking about deterministic simulations of ground motion, broadband, and we'd like to push those simulations to frequencies of relevance to engineered infrastructure. And so we'll talk about simulations that go to 5 or 10 hertz at regional scale as we work our way through this. Just sort of an interesting, these are the two computers that DOE is currently building, I should mention. The Frontier computer is done, was just completed at Oak Ridge National Laboratory. It's been certified, the first exaflop computer. The second computer is about half done, and it's going to be coming online at Argonne Lab. It's going to have about twice that performance projected to be about a 2 exaflop system. But it's interesting, sort of on the ECP website, if you look at the statement on the bottom, to add a little more context to this, if every person on Earth did a calculation once a second and did that for 4 years, that would be the number of calculations that an exaflop machine can do in 1 second, just to give you some context. So these are incredibly big machines, both in terms of speed and memory and size of problems, and we want to take advantage of that. The DOE has always, you saw that DOE has been sort of the pointing end of the spear for the US in development of high-performance computing, and their operational cadence for that has been the following historically. Build a new machine, then spend 2 or 3 years getting the applications up to date and able to run efficiently on that machine. They inverted that process in the Exascale computing project. They said this architecture change is so revolutionary from a software standpoint, we need to start the software development for exploiting these machines in parallel to the hardware development. We can't wait. And I think in hindsight, that was very useful. So if you see the start of the exascale computing project here in 2017, there was a call for proposals, competitive call from the DOE Office of Science that asked for applications to be some of the early users and application developers for these exascale machines, with a couple of provisions. You had to demonstrate the need for actually using this level of computations. That was a really key, important point. So long story short, they selected 24 applications, science applications. They also had 70 projects to develop the software stack to run on these machines. And that's I/O, and that's compilers, and everything you can imagine. And so the science applications were here. They ranged everywhere from modeling small modular reactors to modeling climate change. And we were successful in our proposal to model earthquake simulations. And that was the birth of the Earthquake Simulation, or EQ-SIM, project starting in 2017. Our sort of audacious proposal was to do the following: to model earthquake processes end to end, or all the way from the fault and the fault rupture, propagation of seismic waves through the earth, and the complex interaction of those seismic waves with particular infrastructure on the far end. And so that was really our proposal. And the key questions that we ultimately wanted to address is, what is the regional distribution of ground motions? What does that look like? The site-dependent distribution of ground motions, which ultimately you want to have, as well as the demand on structural response. That was number one. Number two, and this was important for us, the engineers on the project, is how do these incident seismic waves truly interact with an infrastructure system when they impinge on that system? There's really no absolute thing as pure vertically propagating shear waves, except in rare cases. And so what are the implications of having inclined body waves and having surface waves interacting with this infrastructure? How do we deal with that? So both of those things were what we wanted to answer. So, we'll talk a lot more about the details of this tomorrow. 6 years have focused on developing advanced computational algorithms and implementing those algorithms for fault to structure workflow on GPU accelerated systems, specific to GPU accelerated systems. This is just a cartoon of our workflow. We develop our regional scale models. We have to do that very efficiently. From a user standpoint, we run these very, very large problems, massively parallel. Then we have to deal with that data. The good news is we get dense information on ground motion intensity on demand at very fine spatial density. The bad news is we get ground motion intensity at gazillions of points. So we have to make some judgments about how do we utilize that data, particularly as we think about a database like this. And so we're going to talk tomorrow about our mechanisms that we've developed in this end-to-end process for having that large data. Then we ended up having two options we'll talk about tomorrow for analyzing the structure: traditional fixed base analysis, where we just take the ground motions at the surface and apply that to the structure, and then a efficient implementation of the domain reduction method, so we can do this issue of looking at the full inclined richness of the inclined body waves and surface waves, because we can simulate those now. So you're going to hear more about that tomorrow. So where have we gotten to? We've gotten to a place where we can now run some really, really big problems really, really fast. And that was our objective, because we all know that some of our parameters are not well constrained, like the manner in which the fault ruptures before the event, so we need to run multiple realizations and scenarios. So I'm just giving you a couple of snapshots. Our project was focused on magnitude 7 Hayward fault simulations, and the database is going to be initially stood up with a large number of realizations. You can see the simulation on the left for a magnitude 7 Hayward fault earthquake. This simulation at 5 hertz now runs in 3 hours on the Frontier computer. That is enabling, because we can run many, many, many realizations of changing the fault rupture and monkeying with the geology and understanding that parameter space. We can run a magnitude 7.5 San Andreas realization. And this is sort of post-earthquake. This is more getting into the Caesar program now. And you can see the magnitude 7.5 earthquake. We can run that 5 hertz simulation in about 18 hours runtime. For that very, very large domain. So you can see that we're really able to solve these problems now that in a meaningful way, and we can push these frequencies higher. We're just focused on 5 hertz right now. We've actually run a 10 hertz simulation of both of these. And so we could actually push that resolution if you want. So that was a quick summary of the development. Back in 2021, we were use-inspired, I should say, from the get-go in this project, in the EQSIM project. We were always had front of mind, let's build this hammer, but how are we going to transition this hammer into practice in a meaningful way? And that 2021 forum was very helpful in getting the 261 international participants to opine, and the participants ran all the way from the research community, the practitioner community. How can we get this into the hands of both researchers and practitioners in a meaningful way? So the results of that poll are shown on the right-hand side. Number one, the top answer, make an available database of synthetic motions that people can start using and looking at. Don't admire the problem for another decade. Okay, we know there's a lot more development that's got to be done, but let's start getting these motions out there and having critical eyes and professionals and researchers look at these motions and, yeah, these look good and we can use these, or these don't look good and here's why, right? So we need to facilitate that feedback loop. Number two, engineering design code guidance for utilization of these motions. And those in the structural engineering community know there's some initial guidance in ASCE 7, for example, of the utilization of synthetic motions, but that needs to be expanded upon. And so there's more work to be done there. And then finally, don't just compute motions and throw them up on a website. Develop some sort of rigorous acceptance criteria so that we are putting things up that have some quality associated with them demonstrably and quantitatively. So we are working on number one and number three in the CSER project as we speak. So we are working on creating a large number of realizations. I'm going to show you just a quick example. This is the kind of things you can do with simulation, is you can look between event to event variability. This shows two realizations of a Hayward fault rupture. And we have taken a modern, contemporary reinforced concrete building and located it at every grid point of that model, and we've looked at the evolution of the damage for these two things. You'll see immediately in these simulations, there's a very strong directivity effect for these extreme hypocenters. And if you look at the resulting damage on the right-hand side, you see it's very different. Same magnitude earthquake, same fault, but the site-dependent motions are quite different. And we'll bore in a little bit on this tomorrow again. So these are the kind of things that one can begin to look at. So we're going to have 25 realizations. We are evaluating acceptance criteria for those simulations. We'd love to have a magnitude 7 earthquake to model in San Andreas fault, or the Hayward fault. We do not. So we have to do the best we can do. We are stress testing EQSIM by computing measured small events on the Hayward fault earthquake. And you're going to see a presentation and a poster on this. We had 7 events at the hypocentral locations you see in red, magnitude 3 and 4 earthquakes. And so we have done a lot of work in actually seeing how well the model can replicate those ground motions, both in terms of waveforms as well as spectrally. And interestingly, they do pretty darn good up to about 5 hertz. And some, on most sites, some sites, obviously there are some issues, but some sites that really nails it. Number 2, we're evaluating the large events in the following way. We're looking and comparing our simulations with the traditional ground motion prediction equations. And we're not necessarily using those as ground truth because there's a lot of uncertainty embedded in the ground motion prediction equations, but as a comparison, and then trying to understand why the simulations are giving different results in the ground motion prediction equations is a really important exercise. And so Dr. Petrona from University of Nevada, Reno, our colleague working with us, is going to be speaking to this, and she's doing some interesting work there. Then finally, we're also comparing our simulated ground motions with existing commensurate ground motions in terms of similar earthquakes with the same type of fault rupture and the same magnitude, and ideally the same representative geotechnical conditions. So once we develop this database, and there'll be more on this tomorrow, we're going to detail PEER. The intent is for PEER to extend the existing database of measured earthquake motions and augment it in parallel with these simulated earthquake motions. And there's a lot of decisions that have to be made about how to do that. It has to do with the size of the database, how you represent that. We want to make this look as transparent and as similar to the existing database as we can, and so we'll go through those considerations tomorrow. DOE. DOE has been supporting this work, but I'll preempt Joe just a little bit. DOE's motivation is ensuring in their mission space not only the resilience of all their own unique critical structures, one-of-a-kind structures for their programs, but also the programs and energy systems are really going to be important going forward. You probably have heard and are aware there's 6 Earth shots going on for different types of energy systems as well as traditional energy systems. You know, you can't go out and build an entirely new configuration of a system, at least in the West Coast, without ensuring the seismic resilience of those systems. So this is going to be really, really important, some of these technologies in DOE's mission space. So the next 2 days are going to be filled both with technical discussions and applications. I will say this is not only a hybrid workshop in an IT sense. We've got, you know, probably 80 or 90 people online right now from all over the world, and our presenters will be coming in from all over the world. But it's a hybrid workshop from the following standpoint. The first day, we teed up with many leading technical experts, some discussions that will help us solidify our thinking about the database over time. How do we do the source function? How many source functions do we need? How do we gain confidence in these motions and validate these motions? How do we represent the very near surface geotechnical layer? That is a very, very computationally challenging task, and there's multiple ways you can, so to speak, skin that cat. And so we'll talk about that as well. Day 1 and day 2, we're going to have some experts come in, stakeholders, and talk about use cases. It's not just DOE, it's others that will benefit from the utilization of these motions. We'll have that. We're going to hear on day 2, we'll do a more applied dive into the generation of the database and how that's going to be distributed. So we're going to hear from the USGS about the development of the San Francisco Bay Area velocity model. How was that developed? How do we know about that? We're going to see some examples of those small event simulations that sort of test that model. So we'll hear that on day 2. We're going to talk about EQSIM and what the features are of that model, because the way we've implemented the interaction between geophysics and structures is going to impact ultimately how we set up and arrange that database and organize that database. Do we just want to do, initially we'll just provide surface motions. Eventually we want to provide a near surface volume of motion so that people can run the domain reduction method and incorporate soil structure interaction in complex ways. So we'll talk about that as well. And then there'll be discussion from Pierre about how we're actually setting up that database. And then finally, for those that are willing to stick around on a Friday till 4 or 5 p.m., we want to have a wrap-up discussion on community interactions going forward and how we can facilitate in an organized way that continuous feedback loop. And we're thinking maybe an annual meeting where we meet and discuss the progression of these motions and the progression of the utilization of these motions. So I am going to stop there and leave it at that. And before we get into our first technical session, I'd like to invite Joe Degert forward and make a few comments on the DOE perspective as our program manager. So.